А,
Все ли здесь? Does anyone understand Russian here? If not, I can talk in English. Well, both way work.
I think, yeah, there are some people who cannot understand Russian.
Okay, let's start then.
Uh, Okay, today, Professor Vasily Manturov will give a talk about equation of pentagon and invariance of braids. Please start.
Okay, thank you very much. I gave many talks on Ptolemy pentagon, braid invariants and solutions to the pentagon and braid invariants related to them. The novelty today will be related to shear coordinates, which are related to many objects in cluster algebra, in hyperbolic geometry, and other beautiful parts of mathematical sciences. And of course, I will recall many known constructions, how to draw equations, and how we can figure out solutions for many equations without calculating anything, and how we can construct many invariants from such solutions to equations. Okay, and now I will start by drawing the pentagon equation. Why am I saying drawing? Why don't I say to write a pentagon equation? Because when I write a pentagon equation in whatever form, I restrict myself very much. When I write the pentagon equation, I have to say what the target space is, what the source space is. I have to work either with tensors or with groups or with matrices. I don't want to restrict myself to any of such categories. I don't want to use any categories at all. I want to use something I call data. So for me, the pentagon equation is just the following picture. So I draw a triangulation of the pentagon, and then I flip from this triangulation to the neighboring one. So I take one diagonal, and this diagonal remains unchanged, and then I flip the other diagonal. Okay, now I flip the diagonal, which was not yet flipped. So here, this one stays as it was, and this one gets flipped. And then again, I want to flip the diagonal, which was not flipped at the previous step. I mean, this one stays as it was, and that one changes. Then I do it for the fourth time, and then I get here and there, and finally I get this. So when I say an equation, what do I mean by a variable, and what do I want to equate? Well, here, what I want to do is to do a flip. If I have a quadrilateral, I flip it like this. I split my quadrilateral into two triangles by a diagonal, and I flip it here by changing one diagonal to the other. And this is a transformation. Transformation of what? I want to say this is a transformation of data. So here I put some data, and here I put some data. And I should indicate some data transformation law. So this law will be something instead of my variable. So if I were working with groups, I would say this is a group element. Or If I were working in matrices, I would say this is some block matrix. Or maybe I could work with some data which deals with edge length, or maybe squares of edge length, or maybe I can deal with areas or angles, or maybe altogether. And there is some data transformation law. So this is something I use instead of variable. And the equation I'm asking for is that after 5 transformation laws, I return to the initial data. So that's what I require. And today I will give you some solutions to that equation, which are based on different geometrical reasonings. And somehow the fact that this data transformation law satisfies the pentagon equation follows from geometrical considerations, and we may not count anything. Well, we may count, and we may prove something algebraically in matrices, in tensors, or in some other form, but we can guess, we can get a feeling that we will get a solution by just geometrical consideration. And now I want to say a couple of words about how it is related to braid group invariants. Well, frankly speaking, besides this pentagon equation, I really want to have one more equation, which is called the Farr commutativity equation. By a Farr commutativity, I mean that flips in different triangles should be independent. What do I mean? Well, if triangles are really very different and do not share any edge at all, then we can do the following. We may flip the first one and the second next. Like this. Oh, no. For the first one first and the second next. So I flip it here, and then I flip the second one. Like this. Yes, so here I flip the first one. No, excuse me. And then I flip the second one. So I get something like here. Or I can flip the second one first and the first one next. Like this. So this is the picture I'm interested in. And the equation I'm interested in is as follows. So I require that my data transformation rule, whatever the data is, if we apply it this way and that way, then we get to the same result. Well, of course, it is going without saying that I want my data transformation rule, this flip should be to be invertible. So I want this transformation, I want to have the inverse transformation, okay? Now, you see here we have a common point of those two quadrilaterals. But it may also happen that we have a common edge. So we have two quadrilaterals which share an edge. And for this case, I also require that flips here and there are independent. So this is what I'm asking for. And you will see that in some case, this is going for free. And in some other cases, this does not go for free. What do I mean by that? Well, you see, here we have some data. And we may put this data where? Well, we may put this data, for example, on edges. Well, you see, I don't put any data here on vertices. And when I put some data on edges, I may use some data transformation rules. For example, when I flip this edge, I may change the data on this edge. Well, if I really use it on edges. And I may leave the data on those 4 edges as they were. In this case, if I do not change the data on edges, the far commutativity for 2 quadrilaterals sharing an edge does not change. So everything is local, and this edge does not change its labels. But it may happen, and the equation we are going to, the solutions to the Ptolemea, to the pentagon equation we are going to consider today, will sometimes use this edge and change the label of this edge. And then we will have to check something. Okay, now the general principle that I want to formulate now, and this general principle was realized in different situations, and it led to various braid invariants. So if data transformation rule satisfies is invertible, satisfies pentagon, yes, pentagon, and far commutativity, then it yields braid invariance. In comparison with my previous talks, today I want to mention just one new solution, which is related to shear coordinates. You will see this transformation soon, but now when I say braid invariance, what do I mean by that? By that I mean that we consider a braid as follows. We have points on the plane, and having such points, we can create the Delaunay triangulation for those points. Well, generically, the Delaunay triangulation will be a trivalent graph with some infinite edges, and no, this is not the Delaunay triangulation. This is the dual graph. Excuse me. The dual graph is called the Voronoi tiling of the plane, like this. And this graph, well, it just splits the plane into parts so that one part contains points which are nearest to the, which are closer to its center than to any other point. And the dual graph to that Voronoi diagram is called the Delaunay triangulation, and it looks like that. Well, I don't want to pay any attention to the infinite point. Well, it makes some trouble, but I can consider, say, the sphere instead of plane, or compactify something, or put some points, put something inside a big polygon. So this is the Delaunay triangulation. So I connect neighboring points to each other. Okay, points whose domains share an edge, share a common boundary. Okay, so this is a triangulation. What happens with those diagrams, Voronoi triangulation and Voronoi diagram, and especially Delaunay triangulation, if I move point? Well, the most interesting situation is when 4 points are on the same circle. Not any 4 points, but 4 neighboring points. This means that I have 4 points here. They are on the same circle, and there is no other point in this circle. So here are 4 points. And how does the Delaunay triangulation change? So maybe before the flip, the Voronoi diagram looked like that. After the flip, the Voronoi diagram will look like that. So, and in the middle, our Voronoi diagram looks like that, and it's not trivalent. And the Delaunay triangulation undergoes a flip. So we have 2 triangles here, and we have the same quadrilateral with 2 other triangles. With 2 other triangles. So in total, we have such a flip. And now I want to consider some data transformation rule for a flip to cook a braid invariance. What do I mean to cook a braid invariance? I mean that if we consider a braid as a dynamics of points moving on the plane, well, we may assume that this dynamics is generic enough. Then we start from some position where we have a Voronoi diagram, and we end in some and a Delaunay triangulation, and we end in some other position where we have a Voronoi diagram. And please stop drawing and start moving on the blackboard, or the whiteboard. Okay, so we have some points, and as points move on the plane, the Voronoi diagram undergoes flips. So my idea is that I associate some data to edges, or maybe to triangles, or maybe to something else. Please stop moving on the screen. Okay, and I suggest some data transformation rule. For example, if I have data on edges like this, I can suggest the following data transformation rule. This is called the Ptolemy transformation, and it was used many times and discussed by myself. So when I put data on edges, and my data transformation rule is like that. Instead of this diagonal, I get another diagonal, and my y is AC plus BT over X. Well, you see, here my data is something on edges, and my data transformation rule is some rational functions. And what do I require from this data transformation rule? Well, ideally, I want this data transformation to give me an invariant of braids. So I want this transformation to give me the same if I use for isotopic braids. So isotopic braids should give me the same transformation. Okay, and what do I mean by isotopic braids? Well, braids form a groove, And of course, if I want isotopic braids to give me the same, then the trivial braid should give me the trivial transformation. And you see, I want to give you some obvious examples when please stop moving on the screen. I will resume only stop moving on the screen. So if I consider trivial braids, there are some obvious situations. For example, assume my 4 neighboring points are almost on the same circle. Then when I move them a bit back and forth, it may happen that my triangulation changes from here to there and back. So if I have such a change and my transformation is invertible, then okay, such two transformations give me something identical. Okay, so what's next? Well, assume I have 2 quadruples of points, maybe here and there. They may be, we may have 2 quadrilaterals which are disjoint, or which share a point, or which may share an edge. And this corresponds to some points. So here I may have 6 points, or in this case, I can have 5 points, or if, 7 points, and if they are completely disjoint, I get 8 points. Okay, so, and I want to make 2 flips. So first I can make a flip here and then there, or vice versa. So these transformations, they correspond to isotopic braids, because more or less these are 2 independent events. So independent events should commute. And this means that in order to have some braid invariant, these this far commutativity should hold. And finally, I can consider the situation when some 5 points are almost on the same circle, almost, but not quite. And if so, then if they're generic enough, then the Delaunay triangulation looks like that. And if I move these 5 points a little bit, this triangulation may undergo a flip. Then I can move a little bit again, and this will undergo a flip again. And I just move these points very little so that they are always almost on the same circle. So if they are almost on the same circle, then there is no braiding. The braid is trivial, and the transformation, the 5 steps of the transformation, they just give me the pentagon equation. And a detailed analysis says that these 3 conditions, the invertibility, the far commutativity, and the pentagon, are necessary and sufficient for my data transformation rule to give invariance of braids. Okay, of course, I expect that my data transformation rule for a flip is local. So nothing which is drawn outside the quadrilateral changes. So maybe not only the diagonal label, but also the labels on these edges change, but nothing outside changes. Okay. So this is the statement of the problem, and now I want to pass to some solutions. So first of all, I want to mention the fact that Ptolemy yields pentagon, and again, I think this is crucial, and I repeat it, I don't know, maybe 10 times or many other times at this seminar and at other seminars. I think this is very important. Here is the picture. Here is the picture. Do you see my screen? This is my book. Do you see my screen?
Yes.
Yeah,
yeah.
we can see it. Yeah.
Yeah. Okay. So this is my book, Invariants and Pictures, published in the year 2020 by World Scientific, by myself, Kim Son-John, and Igor Nikonov and Denis Fedosеев. And here we have an algebraic proof or check that Ptolemy yields pentagon. So what is the Ptolemy transformation? The Ptolemy transformation corresponds to the well-known fact from school that for an inscribed quadrilateral, the product of diagonal length is equal to the sum of products of edge lengths. So you may just remember AC plus BD equals XY. So where A, B, C, D are edge length in cyclic ordering, and X and Y are two diagonals. So this is the Ptolemy equation, and the Ptolemy transformation is Y instead of X, where Y is AC plus BD over X. So you see here I do it 5 times, and in this picture, I have the following data. Here, A, B, C, D, E are edge lengths, and X and Y are diagonal lengths. And now I flip one diagonal after the other. So here is one flip, here is another flip, and then some third flip, and I do it 5 times. And here, my newborn diagonal gets a label, which is this rational function. I do it 5 times, and finally I return to the labels V and W, which are equal to my initial X and Y. Okay, and how can I prove this fact? Not by checking it step by step algebraically, but by looking at something. Well, you know, there is an argument I gave many times, but then I will justify this argument a little bit. An argument can be formulated as follows. Assume we have A, B, and X to be side length of some triangle. Then assume X, Y, and E be side length of some triangle. And assume C, D, and Y are to be side length of some triangle. If I glue these 3 triangles all together, and if I glue these triangles, and then this pentagon is completely fixed. All data I have in this pentagon, including angles, edge length, areas, and whatever else, are fixed. Everything here is expressed uniquely in terms of any picture like that. So in any diagonals can be expressed in terms of the initial 5 edge length and 2 diagonals, right? So this means that if I start from one picture and go to another one way or some other way, I will get the same data. So data is fixed. What's the problem here? The problem here is that the Ptolemy transformation works for inscribed quadrilaterals only. So this means that I have to impose some conditions here in order to have this things work. And these conditions are really important because for A, B, B, X, Y, and E to be inscribed, we have to do some algebraic equation, right? And the same for C, D, E, X, Y, okay? There was a paper by myself and Wang Jian where we considered some other argument which was called lambda length, and this is related to some other mathematical measurements corresponding to some other objects which still satisfy the pentagon equation. Well, you may look at this paper. This is our paper on the archive. Here is the number 2305-11945. And the idea is as follows. We can fix 7 lengths, make 5 of them to be edges of something, and 2 of them to be diagonals of something. This something will actually be some ideal pentagon in the Lobachevsky space, in the Lobachevsky plane. And then, if we perform a flip, this something will undergo the Ptolemy transformation. Well, this something will be lambda length. And the only thing you have to know is that these triangles are uniquely determined by their lambda length. So this means that if we know lambda length, we know everything. And then we can paste 3 triangles to have a pentagon, and in this pentagon we know everything. And we can flip to any other state to get a solution. Okay? So this is how it goes. And here we can really say that whatever way we go, if we return to the initial position, then we will get the same data. And this is our work with Wang Jian, where we established the photography principle, which allows one to prove that some data transformation laws, like Ptolemy, satisfy some equations, like pentagon, just from naturality conditions. So if we know that some measurements are geometrically transformed according to our data transformation law, then in some cases we know that if we go back, we will get the same measurements. And you see, this happens in many cases, and we can solve many equations like that. And having solved such equations from geometrical considerations, we can then say, okay, if something works, let's prove it by algebra like this. And if we can prove it by algebra, then we can forget that our A, B, C, D, X, Y are length. So, okay, here we have some equation. We have proved some statement from algebra. And this means that those things can become variables. And we can play lots of games and get lots of braid invariants. Now, you see more and more solutions. So our research group is working intensely with the research group by Haig Sedrakian. And Haig Sedrakian is interested and in many nice formulas which could be taught in school, which we are not taught at school. And these nice formulas are well, maybe you know, maybe you don't. So what is the formula for the second diagonal of a quadrilateral in terms of its first three diagonals? No, in terms of its 4 edge lengths and 1 diagonal. So assume we have a quadrilateral with edge length A, B, C, D, and 1 diagonal E. So what about the other diagonal, F? So here is a formula due to Haik-Sedrakian and Aidan Mozaini. So here it is. I think it's hard to remember it by heart. I don't know. I don't remember. But what is not good here is that here we have square roots. But here is a formula. The only thing I want to know is that this formula exists. And I can write this formula to be F equals F of A, B, C, D, E. I have this formula. Okay, I can say that this formula exists. Now, theorem, this formula, if we apply it 5 times from here to there, starting from this pentagon with 2 diagonals, X and Y, I will return to the same values. So here I will have V equals Y and W equals X. I can prove it with eyes closed. Why does it hold? Because of the following. Assume I have a quadrilateral and a pentagon and 2 diagonals. In the Euclidean case, on the plane. Then these 5 edges and 2 diagonals determine my pentagon completely. They determine everything, edges, angles, and so on. You may say that they have to satisfy the triangle inequality. That's right. Now, if we want to know some other triangulation of the pentagon, we can restore everything uniquely. And restore according to which formulas? According to Sedrakian-Mozaini formulas. There is no other way. And this means that if we go 5 times from here to there, we get the information, the Euclidean information. Okay, now what about A, B, C, D, E, X, Y? Well, frankly speaking, these 2 triangles have to satisfy triangle inequalities. But what we are proving here is that I would be happy to say some polynomial, but this is not the case. There are some square roots, and this is a very unpleasant fact. But assume for a moment that some polynomials are equal. So what is the pentagon identity? This is the fact that some polynomials are equal, right? And what are the conditions we impose? The condition is that some triangle inequalities hold. So geometrically, we can prove that provided that some equalities hold, some inequalities hold, some polynomials are equal. So polynomials are equal in some open set. Then these polynomials equal everywhere. For rational functions, well, there is something a bit unpleasant, and that's why there are some problems in getting braid invariance from Sedrakian's work. But And actually, there are lots of problems for students. For example, if you look again at Sedrakyan's formula, you will see that it's very complicated. And now I proved more or less by hand waving that applying it 5 times, I will get the identity transformation. But now, maybe you can use your computer to apply it 5 times. Well, I failed because my computer, when it uses so many square roots, it fails maybe after the 3rd step. So we cannot do it 5 times. But I know that after doing 5 times, I should succeed. Also, there are other mathematical problems. For example, which branch of the square root to take, positive or negative. Okay, so you know that this is a solution. Now, more solutions with eyes closed. We can take this formula f equals f of a, b, c, d, e to be the formula for the other diagonal of the quadrilateral in the hyperbolic geometry. So we take a hyperbolic geometry of constant curvature, and actually you can take any constant curvature, for example, -1 or -2, whatever you want, and say, let's take this formula. Statement. If we apply it 5 times, we will return to the initial position. The same about spherical geometry, and the proofs are all the same. Okay? Well, you may ask me, what about other sort of data? So, for example, I was talking about edge length, but what about anything else? And actually, Ilya Rogoshkin wrote his diploma work based on another approach when instead of edge lengths, we were using some areas. I don't want to get into the detail of this work, but the idea was that we're associating some numbers, we're associating some quantities to areas of some triangles, and when we perform a flip, then we flip these areas. So roughly speaking, if we have a quadrilateral which is split into 2 triangles, then here we have a triangle whose area is a plus c, and b here, there we have b plus d, and here we would have a plus b and c plus d. And working with this data, if we assume our transformation to be linear, we will get a 2x2 matrix corresponding to any concrete flip. So in total, I would have a matrix of size n by n if I have n triangles in my triangulation. For example, 3 in the case of pentagon. So this will lead to some solution to the pentagon by in 3x3 matrices. Okay. And actually, we can experiment and associate data to angles, areas. So the only thing we need is to have some meaningful data transformation rule. And geometry will let you guess how it should work. And sometimes you succeed to solve the pentagon equation. And actually, there is not only the pentagon equation, there are many more equations which can be solved this way. But from pentagon, you can get solutions to the braid group. One more thing which is mentioned in the title of my talk, it is tropical mathematics, tropical geometry. Well, let's return back to this picture and that formula. So you see, in this picture, all we have are Laurent polynomials. Moreover, these Laurent polynomials have numerators with positive coefficients. That means that if we look at this picture, all new variables like z, t, u, and so on will be expressed in terms of a, b, c, d, e, x, y as a ratio of two polynomials. In the denominator, we have a monomial, and in the numerator, we will have only positive coefficients. This means that we do not use any subtraction at all. We use only addition, multiplication, and deletion. And finally, what do we prove? We prove that some Laurent polynomials are equal. Or if we take their common denominator, we prove that some polynomials are equal, right? And we don't use any subtraction. And this means that it can be proved when we don't have any subtraction. And this means that it works not only for fields, but for semi-fields. And there is a very nice tropical semi-field where we don't have any subtraction, but we have the tropical multiplication, which is just addition. So x times y is just x plus y. X divided by y tropically is x minus y standardly. X plus y tropically is the maximum of x and y. So this is something called the tropical field. There is no subtraction. And the only thing we need is the distributivity, commutativity, and associativity. And they all are present. So this is the maximum of x, y. And this is a good exercise for you to check that the tropical Ptolemy satisfies the pentagon. So just write down the tropical Ptolemy. So instead of this standard 3 operations, just use tropical operations and make all those calculations tropically, okay? So you see how the process goes. We use geometry to guess something, then we prove it by using algebra. We forget about our geometrical reasons, and then it works. It should work logically for any field. And since we don't have negative signs, we conclude that we can work tropically and use any semi-field. Okay. Well, now I want to talk about shear coordinates and shear transformation of coordinates. Well, they originate from some cross ratio of points in the hyperbolic 2 space. These cross ratios are well, I don't want to talk. Don't want to get into the detail, but I want to give you just one formula. And having this formula, I want to say this satisfies the pentagon. And not only this satisfies the pentagon, but this satisfies the far commutativity. Okay, so you see, do you see my screen now? So this is the new part, which did not appear in any of my previous talks. Do you see my screen with paint?
Yep.
Okay,
Can.
so this is the data transformation rule. Again, we put variables on edges of my triangulation. I triangulate something, and I put some labels on edges of my triangulation, and then I associate the following data transformation rule. So you see, I have a quadrilateral. Well, maybe I will refrain from drawing A, B, C, D prime, but assume I have a quadrilateral like that, A, B, C, D with one diagonal E. Now, instead of this diagonal E, I want to put another diagonal. But now, attention, when I draw another diagonal, I want to change labels for A, B, C, D. So instead of A, B, C, and D, I want to have A prime, B prime, C prime, D prime. So this differs from what I had before. In my previous pictures, only the diagonal which changes changes its label, and all labels of edges stay the same. This is important. And here they all change. How they change? Well, the new diagonal called E1 will change to will be 1 over E. The label on the edge A and the label on the edge C will get multiplied by E, so by 1 plus E. So here A1 is A times 1 plus E, C1 is C times 1 plus E, and the two other edges will be multiplied by something else. So B1 gets multiplied by E over 1 plus E, and D1 gets multiplied by E over 1 plus E. We can distinguish between A and B by looking clockwise at this picture, but we cannot distinguish between A and C. So the transformation, for E and C should be the same. Again, this is the shear coordinate transformation. And there are two statements which are known to people working in cluster algebras. And these statements are: statement 1, this is invariant under the pentagon. So if we perform it 5 times, we will return to the initial coordinates. And also, this behave nicely with respect to, this respects the far commutativity. Well, you see, the only problem with far commutativity is the case when two quadrilaterals share an edge. You should look carefully what happens with this edge if you do this first and that second. So I want to leave it to you as an exercise. It's really an easy exercise to understand the definition. And as for those pentagons, well, you can do it by hand, but today I did it by computer, just by Mathematica, and here I can show you some script in Mathematica, and you will see that it works. And this goes as follows. We take our pentagon. I want to call its edges and diagonals in a slightly non-standard way. I call the left quadrilateral, maybe you saw it, A, B, C, D. So A, C, and D are edges of the pentagon, and C is one diagonal. And E is the, no. A, C, and D are edges, and B is an edge of the quadrilateral, and E is the diagonal of the quadrilateral. So in total, we have A, C, and D to be edges of the pentagon, plus we have two more edges. I call them, I think, P and Q, and we have two diagonals, B and E. And now you should see my Mathematica script, okay? So my Mathematica script, so here we have the transformation of shear coordinates, which is called A. So we have A, B, C, D, E here. And I just do this shear coordinates. Okay, now I have my coordinates A, B, C, D, E, and I perform their flip to A1, B1, C1, like this. Then I use another flip, and here P and Q come into play, and I call the resulting things here P1 and Q1, but C, B, C, and E are already changed. So here I had B, C, and E, and I get B2, C2, E2. So here is the second step. Then again, I perform the flip course. Well, I should have drawn coordinates, but I was a bit all pictures, but I was a bit lazy. So here is the third step. So here is the fourth step, and after the fifth step, I get, you see, I get the same A, B, and E, the same P and Q, and C and D appeared in the previous step. So you see, I returned to the initial position, and that's the proof by Mathematica. And an exercise for you, do the same for the tropical case. So you see, as again, as in the case of the Ptolemy satisfies pentagon. Since it has no subtraction, we can do it tropically. Hence, tropical Ptolemy satisfies pentagon. The same for shear coordinate transformation. Shear coordinate transformations satisfies pentagon, plus it satisfies the far commutativity. The second statement, the last statement, is not obvious because not only the diagonal changes, but edges do change. Yes. And now, since this transformation does not use subtraction, everything can be done not only for a field, but also for a semi-field. Hence, it works tropically. Hence, shear coordinate transformation rule, taken tropically, I would say tropical shear coordinate transformation rule, also satisfies the pentagon and far commutativity. And this means that all those transformations give rise to braid invariants. So now it's a work in progress. I'm writing a paper, and this paper was inspired by Mikhail Shapiro. So the paper I'm writing is that Ptolemy and tropical Ptolemy satisfy shear coordinate transformation and its tropical counterpart satisfy the pentagon. And the rule for the tropical formula for the shear coordinate looks like that. So you see, instead of multiplication, we use plus. Instead of plus, we use maximum. Instead of division, we use subtraction. And instead of 1, we use 0. The operation, the element which is neutral with respect to our tropical multiplication. And in our case, the tropical multiplication is the addition. So you see, we can guess lots of solutions to the pentagon equation, and yet some more. And having that, we can get lots of representations of the braid group. Okay, here you have lots of problems and lots of exercises to work with. So you can take any situation, any picture, and check your favorite equation that it does satisfies the pentagon. Sometimes, as in the case of Hayek-Cedar-Akans solution, it's hard to check something by computer, even if you know it's true. It may look paradoxical, but it's so. So we know that it should be true, but the computer doesn't work after 3 steps. Also, there are lots of questions. There are lots of things to calculate. You should calculate braid invariance. So you can take a concrete non-trivial braid and calculate this invariant. So usually when I suggest students to do something with a braid, I suggest the following. Take a 5-strand braid with which is inside of the triangle. So 3 points remain fixed, and 2 points move one around the other. So we have some picture like that, and this picture undergoes 6 flips when this point returns to the initial position. And starting with some labels, you see, we will have, I think, 1, 2, 3, 9 labels. You will get 9 resulting labels, which are expressed in terms of the initial one. So you can calculate such braids, braid invariance. Well, and then who knows, maybe you can get to knot invariance and maybe some other things. So there is a lot of work in progress to do. Okay, so this is what I was going to say today. Thank you very much.
Thank
So-
you.
Okay,
Thanks. Happy to show. Bye.
are there any questions or comments? Okay.
Not so fun.